Everyone, you might recall a little while back hearing news that the SHA-1 hash function had been broken, and the amount of publicity and attention given to this is an indication of the importance of the primitive here, hash functions. So remember, we've been discussing that in modern cryptography we build schemes in a modular Lego-like fashion, starting from low-level building blocks that we call atomic primitives to reach higher-level ones which solve problems of interest in applications. Our first example of an atomic primitive was a block cipher, and we saw how to use that to create symmetric encryption, which is one of the most important end goals. So hash functions are another atomic primitive, and we'll study them in the same kind of style we studied block ciphers, which is kind of empirically trying to understand what they're trying to do and how they're built and what options exist and what properties they have. So cryptographers over time have designed lots of hash functions. We can distinguish a few series. There's the MD series with a number of hash functions in it, the SHA-2 series, which includes the SHA-1 hash function, and now the most modern, the SHA-3 series. And they vary, for example, in their output lengths and also in their security properties, but their primary purpose that they have in common is collision-resistant compression of data, meaning they must take long inputs to short outputs, and yet it should be hard to find two inputs that map to the same output. But they have many other purposes and properties as well. And indeed, in design, hash functions are often treated like a magic wand. We throw them in to accomplish all kinds of tasks and view them as having the ability to randomize the inputs to which they're applied. Nowadays, specific applications where hash functions are important include digital certificates in the public key interest infrastructure as used by TLS. So, for example, if you get or try to access a website like www.snapchat.com, it authenticates itself through a certificate, and that certificate involves a digital signature, which in turn involves a hash function. Hash functions are used in Bitcoin for proofs of work. They're used through HMAC for data authentication, which in turn is used in TLS, and there are many more such properties. It's ironic that the acronym SHA stands for Secure Hash Algorithm in light of what we saw happen to SHA-1. So the basic element of interest here is a collision. So suppose we have a function. This is a fixed function from some domain D, and outputs are n-bit strings. And a collision is simply a pair of inputs in the domain for which the function has the same output. However, it should be non-trivial. Clearly, if x1 equals x2, h of x1 equals h of x2, that's not interesting. So we insist that the two inputs be different. Okay, now if I have a function like this, no matter what that function is or how you try to define it, as long as the size of the domain is more than the size of the range, the latter here being 2 to the n, we're talking about domains of size in excess of that, there must exist two inputs that have the same output, and hence there must exist a collision. This is relatively obvious. Mathematicians call it the pigeonhole principle, which says that you can't squeeze n+1 pigeons into n holes without one hole having two or more pigeons. Indeed, if you have, for example, 3 inputs, you can send and 2 outputs, you can send the first input somewhere, the second input somewhere else, but you're stuck on the third one. You'll have to send it to an already used output. So the intriguing aspect of cryptographic collision-resistant hash functions is that collisions will exist. In fact, lots and lots of them will exist because the domains will be significantly larger than the range. But they are not easy to find. The computational efforts to find them are rendered prohibitive. we can move now to giving a formal definition. And in this, we will, more generally than the last slide, consider a family of functions. Recall that just means that we have a 2-argument function h, whose first argument is drawn from a space called the set of keys. The second argument is an actual input, and it outputs a result in some range. We've seen as examples of these PRFs, block ciphers, and so forth. And syntactically, it's the same kind of object, but we are looking at a different security metric. Also recall that when we fix a key and subscript h by that, we're talking about the induced function from this domain to the range, which evaluates the 2-argument function with the key fixed to the choice here. Our game, called collision resistance associated to the family h, will in initialize pick a key at random from the key space. This we've seen many times when we're defining key recovery security, PRF security, and so forth. But now we see something novel, which is that there's a return statement with k. What that means is that the adversary is actually given the key. Unlike key recovery or PRF security, here we are not asking the key to remain secret. The adversary in its attack has it in its possession. Otherwise, the game is quite simple. There are no non-trivial oracles. The adversary simply computes along with the goal of finding a collision for h sub k. When it thinks it's done, it outputs a pair of points x1 and x2. Alternatively, it calls finalize on inputs x1 and x2. And the game checks that they form a valid collision. And if they do, then the adversary wins. So what does the game return? Whether hk of x1 equals hk of x2. That's a Boolean reply over here. Of course, the additional checks it makes to ensure non-triviality, if the 2 points are the same, the adversary tries to cheat there, then it says, no, that's not a valid collision. And although perhaps redundant, the game here includes the check that the points really do belong to the domain of the hash function here. It's redundant because really we should only consider adversaries that do provide points in the domain, but there's no harm in writing it down. When the adversary plays this game, it may or may not be successful in finding a collision. So finding a collision is an event that can happen or not happen. It's captured by the game with this adversary returning true, and that will have a certain probability of happening because there's a random choice over here, and also potentially because the adversary is randomized. And that number is the adversary advantage. The subscript is the name of the notion, collision resistance. We put h here because it's a metric of security for the family of functions h, and a here because it's the adversary's advantage. And we've seen by now many such advantages. We kind of know how to interpret them, and we know that high advantages mean adversaries are doing well, low advantages meaning they're not, and so forth. But before we go on, so let's recap a couple of points here that make this a little different. And again, one to emphasize is that this syntax, which is something new, when you have a return statement and initialize, whatever is here goes back to the adversary, in this case the key, making it non-secret. So let's see if we can build a collision-resistant hash function. So as an example, let's fix a number n, say 2 to the 2 power 56. I will use the set of numbers from 1 through n as the set of keys, and the set of all non-negative integers as the domain. It's actually an infinite set, that's okay. The range is the set of all numbers from 0 through n minus 1. And the way the hash function works is given input a key from here and x from here, it just returns x mod k. Okay, is h collision resistant? What that means is you're asked, can you design an adversary that easily finds collisions in h? It's not hard. intuitively why. One reason, here's an equation that's true. If I take some x and add k to it, and then take the result mod k, since k mod k is 0, I get back the same x. So x plus k and x form a collision. So what can the adversary do, for example? Again, as usual, we specify it in pseudocode. And here we see how we render the new element of the model that the adversary has k provided to it. It appears as an input. So the adversary here gets the k from the game. And now it'll pick some point in the domain. It happens to pick 0. It adds k to that to get the second point, and it returns that pair. And this adversary will have advantage 1. Okay, so that should illustrate how we find collisions. Here's another example, maybe a little more involved, where we say, okay, we've kind of understood that you don't get cryptographic security so easily from scratch by just writing down little formulas. You need to start with something non-trivial, but we have such objects. We have block ciphers. And so it's quite natural to say, let's use a good block cipher as a tool and from it construct a good collision-resistant hash function. So we might use AES over here. So here's our design. When we want to hash under a key k an input, where our input length is going to be twice the block length of the block cipher, but the output length will continue to be n, the block length of the block cipher. We break our input into 2 halves, each n bits, and then we apply the block cipher with the key k to the first half, add in the second half, and reapply the block cipher. So that's our candidate, and this output is returned. But the claim continues to be that this is not going to work. And let's illustrate why that's the case. To do that, we have to design an adversary specified in pseudocode and argue that it has a high collision resistance advantage. So whenever we approach questions like this, the first thing we need is, having understood the game, we know our search is for 2 inputs with the same output. Now, each input is 2 blocks long. So we will have x1, which is 2 blocks long, and x2, which is 2 blocks long. And we are free to pick both of these, which means all 4 blocks, any way we want. And our goal is to ensure that if you run h on these 2 inputs, you get the same output. So think of that as an equation. This is what the output is. The output on x1 is this. The output on x2 is this. We want these 2 things to match up. So we can now see it as equation solving, but we have a ton of unknowns that we control. So we have 4 unknowns and just 1 equation, and we get to pick all the 4 unknowns. So can we make the equation come true? Sure, and here's a method which is now encapsulated in this adversary. The adversary gets input the key k, and it picks x1 arbitrarily, the entire x1, meaning both blocks. So happens to set it to 0 for the first block, 1 for the second block. So this has been determined. Now it sets x2 in the second block to be 0. In other words, it determines this now and sets it to be 0. At this point, only 1 unknown remains, which is the one over here. And that it can solve for. Why is that? Because E sub k is a block cipher. It can compute all of this plus this and just run EK inverse on that. And that will give you something satisfying the equation. So when you return x1 and x2, you will have an advantage of 1. And here note that we used the fact that the adversary knows the key because it had to compute EK inverse here, and it had to compute EK here. And we also use the fact that E is a block cipher because we invoked this inverse over here. Now, we're not going to give up on the idea that we can go from block ciphers to hash functions, but what we've seen is this particular way of doing it is not very good. So here's an exercise in which we try to continue to use a block cipher to build a hash function, and it's a little more involved and tries to get around the prior attack, but nonetheless you'll show that it doesn't quite work. Now, for block ciphers or families of functions aiming to achieve key recovery or PRF security, the key is of course crucial. That without that secret key of a sufficiently large size, you wouldn't possibly be able to have security under those metrics. That's not quite true for hash functions. So in fact, practical hash functions are keyless. We would like to discuss those, so we view that as a special case of a family of functions in which the set of keys is trivial. It consists, let's say, just of one key without loss of generality, the empty string. When that's the case, we will tend to omit it in notation. So we'll just write H as having one input instead of things like this. And indeed, all of the hash functions that we've mentioned and which we'll see a little bit more about later are keyless in this way. Okay, so how then should we design hash functions? Well, the way cryptographers do this is they go back to the same basic principles as used in block ciphers, starting from scratch and using bit operations and numeric operations combined with some structure at a high level which is well understood and produce our hash function. So to see what it looks like, let's take a quick look at SHA-256. This is the currently most popular hash function, the successor to SHA-1. It is keyless, so we'll write it as having just one input, no keys occurring here. The input is any string whose length is strictly less than 2 to the 64. So I'm writing this as notation for that set of strings. But the output is a fixed length, 256 bits. Now notice that 264 is really big. You're very unlikely to ever hit inputs that long. So somehow in practice, you think of SHA-256 as taking arbitrary length inputs. But formally, it looks like this. Now, the first step is to apply a little routine called SHA-pad to the input to result in a message M whose length is a multiple of 512. So length of M mod 512 is 0. And that is done so that we can break M into 512-bit blocks. And we'll be processing M in a block-by-block manner. And so we'll write the blocks this way, and N now is the number of blocks. Next, SHA-256 defines some constants. There are 8 constants written here. Each of them are 32 bits long. And they're fixed in the sense that these particular values are hardwired into the code. We string them together, so we get 8 times 32, which is 256 bits. And here we have a quantity that we call H0, kind of an initial vector. Now we're going to keep updating this value, creating H1, H2, and so on in the following fashion. We have, as a subroutine, and this is the heart of SHA-256, something called its compression function, which maps 512 plus 256 bits down to 256. In any round, we feed this the current message block and the prior H value. This H value is called the chaining variable. And it produces the new updated chaining variable. So in the first round, this is M1. This is our H0, the constant from here, and we get H1. Next time, put M2 here, H1, and we get H2, and so forth. And we simply return the last value of the chaining variable. Okay, that's it. We'll see later that this high-level structure is well studied and well understood and has provable security guarantees. And that's an important part of why it's used here. So now we can look a little bit more at some of the internals of this. So here is a description with more detail of how the initial padding algorithm worked. Remember, its job is to take the input and expand it as necessary so that its length is a multiple of 512. How does it do that? It takes the input and it pads it out with stuff. And the padding is done in a specific way. First off, at the end, we put a 64-bit binary representation of the length of the original string x. Here we put a 1 as a kind of separator value. And then we put enough zeros to make the whole thing have length a multiple of 512. This calculation tells you how many zeros you will need. That's sharp-add. The next thing in the code we saw in the prior slide that one might ask about is, what about all those constants? Remember, there were 32-bit words and they were hardwired into the code. Well, it turns out they're obtained by taking the first 32 bits of the fractional part of the square root of the prime numbers. So you take the prime numbers one by one, like 2, 3, 5, 7, 9, etc. Take square roots, look at the fractional parts, and then use that to create these constants. Interesting. Why would they do it that way as opposed to any other way? Is it real something particularly random? Why couldn't they just pick things at random? I'm not sure there is public explanation for this, but one thing that comes to mind is that we know that standards can get subverted. So we have seen that government agencies have at times planted backdoors in standards and then worked towards having them adopted. So if there were no explanation or way to derive these constants, someone might suspect something like that. And so in some ways this thing allays those fears and it says, no, we're obtaining them by this specific formula. Perhaps, I'm just guessing there. Okay, but in that high-level description of SHA-256, we have so far omitted the most important part, which is the compression function. The compression function is the workhorse that block by block eats up the message, always compressing those 512 bits down to 256 for the next round. So we now need to think how that works. Well, this compression function is itself a collision-resistant hash function. The only difference is that its input has a fixed length of 768 bits. How does it work? Its input is viewed as having two parts. This is the message block, and then there's the chaining variable over here. So what it starts out by doing is running an algorithm which is actually a block cipher. So it turns out that here we see again a connection with block ciphers. Inside SHA-256 is a block cipher with 512-bit keys and 256-bit blocks. We'll denote it as E SHA-256. Okay, so that is applied with the message block as the key and the chaining variable as the input, and that gives a 256-bit output. Once you obtain that, you break it up into 8 words, each 32 bits. You also break the chaining variable here, which is also 256 bits, up into 32-bit words. And then you simply add these word-wise and put the result together. These additions are done modulo 2 to the 32. We now have our 256-bit string here, and that's the output. So once we've actually looked at the internals of SHA-256, we see that even that is quite simple. It just calls on another key primitive inside. This structure is also well studied. It's called the Davies-Meyer construction, and at some point we'll talk about that as well. Okay, so that leaves us with, well, what's a block cipher? Well, block ciphers are things cryptographers know how to design. So here they have designed this specific one. And we won't look at this in too much detail. It's very similar in style to other block ciphers. So again, it takes two inputs. From a block cipher perspective, the first one is a 512-bit key. The second one is the 256-bit input block. So it breaks the 512-bit key into 32-bit words. And now it initializes these variables W with those corresponding words. It then creates a whole bunch more W values so that we have a total of 64 of them. And these are created by applying certain functions in certain ways to prior W values. We similarly break the input here into 32-bit words. And then we create this state variable S, which is 256-bit long, by initializing it to be these V values over here. Now, block ciphers tend to use rounds. We've seen that before. This one has 64 rounds. Remember, DES had 16, AES had 10, so there's rather a lot of rounds, but the rounds are relatively simple compared to these other block ciphers. And here it shows what it does is it defines variables T1 and T2, and then it defines, it updates the state. So remember this 256-bit state, which has components S0 through S7, and now we update all of those. And then, so when we are done with the 64 rounds, we look at the final state variable and we return that. We're not going to discuss exactly what are some of those functions that are called. The description of SHA-256 is public. You can look it up on Wikipedia or anywhere else, and you can easily see any details that you would like there. It's interesting that, again, constants are involved, and the constants now are relate to cube roots rather than square roots of the prime numbers. Okay, so of course, there are many questions here with regard to why certain choices are made. We'll be able to justify some of these choices. Others are more empirical and justified by the desire to evade different attack strategies and things like that. Maybe another thing worth noticing or commenting on is that although a block cipher is used, it's used in a rather unconventional way. So far, we've only seen block ciphers used with secret keys. But here there's no secret key, and nonetheless we're using a block cipher. And we'll have to puzzle out what that might mean. Okay, so SHA-256 is very much out there. If you want to play around with it, you can on the internet find these SHA-256 calculators. So here's a URL where you can do that. I went there and I typed in some text. You hit calculate SHA-256 hash, and you can see the result. But you can also find software, OpenSSL or other things, and run the hash function. It runs very fast. You can also find lots of timing analysis out there. Now, we've already mentioned that there are some very interesting and important usages of hash functions, like creation of certificates, HMAC. It's also used for key derivation in TLS, Bitcoin. But all of those are kind of ahead of us. We need more machinery before we can talk about them. And so in order to not leave us hanging without any concrete application, let's discuss some other possible uses of passwords, of hash functions, specifically password hashing, which is a very important application. So the application setting here is that as a client, you have a password and the server stores it. So this is very common, like you're accessing Gmail or any number of internet services where you have a username password. And you expect to authenticate yourself by conveying the password to the server, who checks that it matches the one they associate to your name, and then they give you access. Now, just to be clear, you of course don't send the password in the clear. This is sent over a TLS connection. So while the server does get the password, nobody else should be able to do that. So that's not the problem we're worried about. But there is another problem, which is that as long as the server is storing passwords on its system, there's a vulnerability due to the fact that that system can be compromised. In fact, server breaches are quite common, and we hear routinely news of them. You might have got email that you were involved in one of these breaches, like the Yahoo one or the Equifax one. And the question is what we can do to help protect passwords in the face of the fact that servers are going to get compromised. So what's usually done instead is that the servers don't store clear text passwords. They store their hashes under one of these hash functions. The client will still convey over the TLS channel the clear text password, but the check now is hash what's obtained and check that it matches up with the stored hash. So server compromise now results in the attacker getting the hashed password. And our goal should be that that hash does not reveal the original password. In other words, it should be hard for an attacker to reverse the hash and get back the original password. And this is true as long as H is one way. One way stands for not easy to reverse. But that turns out to be a consequence of collision resistance. And so this is one sort of use of collision resistance. So this story shouldn't end there, because it fails to state that there is another important attack route, but that results from the fact that people often choose passwords poorly, that they fall within a certain small set of words called a dictionary that can be exhausted. And thus it's possible to brute force a set of popular passwords and thereby from the hash actually recover the password. But if you have a well-chosen password, you should be able to avoid that. So now that we have maybe a little sense of a few things we can do with hash functions, let's start looking at security. We have a candidate hash function, SHA-256. How secure is it? So when we approach the job of finding collisions, a security metric, remember, is collision resistance, we see once more that our old friend or old enemy, the birthday attack, comes into play. And it finds collisions maybe quicker than we would naively think they can be found. Just like exhaustive key search for block ciphers, the birthday attack for hash functions is generic and ubiquitous. It's not preventable. It works on any hash function. The only thing we can do is pick parameters so that its cost becomes prohibitive. So let's fix our hash function. It has k-bit keys, inputs from some domain D, outputs of length n, and the domain is assumed to be larger than the range. The attack is parameterized by a number q called the number of trials. So we think of an adversary associated to this number q. Remember, it gets the key as input. How does it proceed? It picks q inputs, let's say at random, from the domain. And then it just hashes all of those. So now it has q hash values. And it simply sees whether within those q hash values, some two are the same. And so that's it. So it tries to find a pair I and j such that the outputs yi and yj of the hash function are the same, but the inputs are not. And if that's the case, xi xj is a collision. If you found it good, you win. Otherwise, you just return a fail symbol. So why is the birthday phenomenon arise here? Because you're looking for two things being the same across a list of q things. And that reminds us of the birthday problem, although the connection is going to be more subtle than just that. So the birthday analysis is usually understood as telling us that the collision resistance advantage of this adversary is the collision probability for throwing cue balls into 2 to the n bins, which by estimates we've made should be roughly 30% of q into q minus 1 over 2 to the n. This is what's understood in the literature and in practice. The takeaway is that once the number of trials hits about the square root of 2 to the power n, which is 2 to the power half of n, you can find collisions. And that tells us that the output length is a very important determinant of how much security you have. Okay, so now we get into something which is maybe a little neglected when you see discussions of this birthday attack in the literature, which is that what sort of analysis or proof justifies or validates the formula we said is true for the advantage of the adversary. So let's try to analyze this attack a little more. So here I've rewritten the attack, except I've dropped a few things for simplicity. So in particular, remember that our test was we want two outputs that are the same for different indexes, but the inputs must be different. I'm going to drop the condition that the inputs are different because it's extremely likely to be true that all inputs are different, simply because D is a much larger set than the range. So if the size of D is much more than 2 to the n, and we can ensure that for any reasonable hash function by just starting with long inputs. For example, for SHA-256, we would use 512-bit inputs. Then this will make very little difference. And so I've simplified things to this. And I'm not worried about returning the collision. I'll just set a Boolean flag when it happens, because what we're interested in is just the probability that that event is true, because then the adversary is successful. Okay, now I'd like to analyze this with the birthday problem. So let's recall what the birthday problem would be in a similar context. It would say we have q iterations in each of which we pick a random n-bit string. And then I ask, are there two distinct indices for which those two strings are the same? This is throwing q balls into 2 to the power n bins. And we declare collision to be true if that happens. So what's the probability of a collision? Well, by definition, we have a formula for this. Our study of the birthday problem says this is the collision probability for throwing q balls into 2 to the n bins. Okay. But now we want to think about our adversary in relation to this. So let's write here the code for our adversary. It also goes through q iterations, and they're defined this way. In them, y sub I is the hash of x sub I, where x sub I was chosen at random from D. This part of the code here is the same as here. It's just looking for two different indices with the same output. And they're asking what's the probability of a collision. Now, the understanding from a few slides back and then understanding in practice in the literature is that this is the same as this, right? But what you see is that actually that's not true. So the code is different. On the left, the y sub i's are random, and on the right, they're not. They're results of applying a very specific function h with a certain key k to randomly chosen points in the domain. That is not necessarily the same as this. So why or how can we conclude that this formula carries over here? In fact, interestingly, the answer is you can't in general conclude that, and the conclusion in general is incorrect. But you can at least say that it's correct if your hash function has certain properties. So let's go back to our hash function, which has drawing its inputs from this set D. And I'll make a definition under which I call this regular if the following is true. Whenever I have a point in the range, it will have a certain number of pre-images under h sub k once I've fixed a key k. Okay, I denote that set as follows. So with k fixed, hk inverse of a point y in the range is the set of all inputs which under hk map to y. This means I've broken the domain D up into these little disjoint sets, which are all of these types of sets. Okay, now how many pre-images would a range point have? Who knows? It depends on the function. It could be 0, could be 1, it could be everything in here or something in between. We will call H regular if the size of that set is independent of y. So every point in the range has exactly this many pre-images. So, and that's the regularity structure there. Moreover, this is true not only for every point in the range, but for every key. So the structure holds across all the keys. Well, why do we like these kinds of functions? Because now, consider the two processes in which we're interested. One was to pick y at random from 0, 1 to the n. The other was to first pick a domain point at random and then run the hash function on it under key k to get y. And we're interested in how y is distributed across these 2 points. And remember, we said earlier that in general, the distribution is different. But the claim is that in the case that the hash function is regular, they're actually distributed the same way. How can you see that? Well, when you pick x at random from here and you map it, you can think of it as being chosen at random from the pre-image of whatever you get. And since these pre-images all have the same size, a simple calculation shows that the probability of getting any particular y through this is exactly 1 in 2 to the power n, exactly as you would like over here. So the conclusion is that as long as you have a regular function, then the two games or processes we saw earlier coincide. And now the analysis of the birthday attack does apply, and the collision probability in our birthday attack finding collisions is exactly c of 2 to the nq. And so indeed the advantages is claimed, and the adversary will find a collision in about 2 to the power half of the output length number of trials. Okay, but what about functions that aren't regular? After all, they don't have to be, and the SHA-256 function, for example, may not be regular. Interestingly, if H is not regular, the attack only gets better. So maybe one way to see intuitively why that's true is take an extreme example. What is an example of a hash function that's extraordinarily non-regular? It would be the hash function which is constant. So for every point in the domain and every key, the output is always 0. It would be very easy to find collisions in that hash function. Any 2 inputs work, right? And the birthday attack will find that very quickly. So if you run the birthday attack, it succeeds much faster than you would expect. And in general, this is true. The less regular your hash function, the faster it succeeds. This is also something that's not too well appreciated in the literature and practice, perhaps because the expectation is that the popular hash functions out there are believed to be close enough to regular that none of this matters. But it's still interesting because, for example, there is no natural way to test regularity of these functions. In fact, since we can't find collisions except, well, in some cases we can, but it still takes some effort, it's not clear how you would even test how regular these functions are. So all in all, there seems to be some little bit of a gap in our understanding here, but heuristically at least, things seem to be what we expect. So let's summarize a bit. We certainly have some theoretical concerns or angles to consider, but from a practical perspective, the birthday attack is the best generic attack against hash functions, and it finds collisions in time about 2 to the power half of the output length, and it applies in particular to all these popular hash functions. Now, you can see historically that as hash functions progressed, they tended to have an increasing output size, and this was a reflection of the need to make the birthday attack take more and more time. Also, these hash functions tend to come in families with different options for the output size. So here, the SHA-2 series, you could have a 128-bit output, 160-bit output size like in SHA-1, or 256 like for SHA-256, or 512 for SHA-512. SHA-3 continues to have such options. And so here you see the birthday attack times for them. So now we can see that kind of the goal of hash function design is to say, okay, we can't avoid the birthday attack. Let's just make sure there's nothing better. So the purpose of the design is to make sure that the best possible attack is the birthday finding attack, so that these numbers actually represent the real and best possible times to find collisions. We'll see as we go on how or to what extent people have been successful at that design. We already know, of course, that in some cases they haven't. Before we do that, let's take a bit of a closer look at the design, in particular, some of the principles that go into SHA-256 and many other hash functions, because many of them can be validated, and we see that there is structure and theory behind them. So recall that SHA-256 had inside it its compression function. So in general, a compression function is itself a family of functions. It has a key of some length, and it has inputs of some fixed length, which we'll view as the sum of two numbers, a block length and a chaining variable length. So for example, the block length for SHA-256 was 512, chaining variable length was 256, and so we get a 768-bit input here. And the output will have length n, the length of the chaining variable. So the SHA-256 compression function looked like this, except since it's keyless, effectively k was 0. We tend to write things this way. Having fixed a key k, we view the input as broken into two parts, a b-bit part, which is a message block, and a n-bit part, which is a chaining variable. But in the end, of course, the compression function just concatenates them to produce the output. So we saw in SHA-256 that the compression function was iterated in order to get the final hash function. So let's abstract out that, and we'll call it a transform, the MD transform. Its job is to turn a compression function into a hash function. What is the difference, or what does that mean? A compression function does hash. It's just that it hashes inputs of a fixed length like 768. But I really want to hash inputs of a much longer length, and that's what a hash function does. So when you have a compression function like this, view it as given, and let's take a larger set D, such as the set of all strings whose number of blocks is 2 to the power this number b minus 1. A block here will have length b bits. So the MD transform will build a hash function with that set D as a domain, a very large set. Of course, you might consider many ways to do something like that. Why are we doing this? Because we have this rather nice fact, which is that if our compression function is collision resistant, automatically that property is inherited by the hash function itself. So to back up a bit, you can talk about collision resistance for both little h and big H. It's a perfectly valid metric to apply to either. Let's say we have studied and somehow established a compression function that is collision resistant. That allows us now automatically through this transform to obtain a hash function that's collision resistant. And what's been accomplished is that the problem of hashing long inputs has been reduced to the problem of hashing inputs of some fixed length. So this will be an easier task to figure out how to do, which is to hash inputs only of some fixed length. The merits of this fact are that you've reduced the work you have to do in terms of studying attacks and validating security. In particular, you no longer need to search for attacks on the hash function, because as long as the compression function is good, there's a proof telling you the hash function is good. So you can spend your time cryptanalyzing the compression function and validating its security. Put another way, you're guaranteed this is good, but under the assumption the compression function is good. And for this reason, this paradigm has been used in the design of at least the first two series, the MD and SHA-2 series, but SHA-3 did switch to a different paradigm. So let's describe this transform and also prove this theorem. So again, we start with our compression function whose parameters look like this. We want to build a hash function where D is the set of all strings with 2 to the b minus 1 or less blocks. Now, some notation. We're going to take messages which belong to this set D. So their length is a multiple of the block length B. Accordingly, we let this notation be the number of blocks, each block being b bit long, and we can now parse a message into blocks like this. So L is the number of blocks. Okay. Another piece of notation, once we've done this, it turns out that the number L here needs to enter the design, and we'll represent it as a block through this notation. So this notation means take the integer L and turn it into a b-bit string. This requires that L be in this range, otherwise you can't turn it into a b-bit string. And this is actually an explanation of why L, which is the number of blocks in the message, is restricted to be at most 2 to the b minus 1 in the design. Now, one might notice that here the domain is not strings of arbitrary length, but only those whose length is a multiple of b. In that sense, it's more restricted than the full SHA-256. But remember that SHA-256 started with the SHA-pad that brought the length to a multiple of b and then ran what we're going to call MD. So here now is how the transform works. So the algorithm is best seen through the picture. Let's say we have a message of 2 blocks, so 2 b-bit blocks. We'll fix some value here. For simplicity, I've here set it to just the string of all zeros, but SHA-256, remember, choose this to be some constant created through the square roots of prime numbers. So you can fix it any way you want, but you fix it. You run the compression function. Here the key is just fixed throughout, so we basically ignore the key. This will give you another n-bit value here. You now take the second message block into the top of the compression function, this chaining variable into here, get the next value of the chaining variable. Now at this point you have exhausted your message. We had a 2-block message, but you don't stop there. You throw in a third block whose content is the number of blocks in your message, here 2, written as a b-bit binary string. With that as the third block, you do your last compression function iteration, and that's your final output. Okay, so that's how it is pictorially. Here we render it in code. We compute the number of blocks in the message. We append to this message one more block, which is the number of blocks in the actual message encoded as a b-bit string, initialize the chaining variable, and then the loop performs its iteration m plus 1 times and returns the final value. We now have our design, and here's the result about it. It says that if the compression function is collision resistant, so is the hash function. How does it say that? Fix your compression function. Let the hash function be obtained in the way we just described in the last slide. Now, suppose you're handed an adversary attempting to violate collision resistance of the hash function. It will have a certain advantage. We're saying that we are able to build another adversary attacking the compression function, again in the collision resistance metric, with an advantage at least as high as this. With whatever probability this adversary A, big H, finds collisions in the large hash function H, this adversary will find collisions in the smaller compression function little h. Furthermore, the running times of these adversaries are about the same. How do we draw our conclusion from this? To say that we assume little h as collision resistance effectively means we think of this as small. But then the equation tells us this is small too, and we interpret that as saying the big hash function h is collision resistant. Okay, so this is by now we've seen several examples of reduction-based results and proofs, and this is another such theorem. Historically, it's actually one of the first. It even preceded the ones we saw earlier, and its proof is quite simple. In fact, its proof is a good deal simpler than ones we've already seen, so we'll go through it and hopefully it's easy enough to see. Before that, a couple of remarks that might be of interest relative to this theorem. So this theorem is saying that collision resistance of the compression function is a sufficient condition to ensure collision resistance of the hash function. So as long as I'm guaranteed little h is secure, so is big H. But what if little h is not secure? Does that mean big H is not secure? Not necessarily. Or put more mathematically, the condition of little h being collision resistant is not necessary for big H to be, right? So possibly big H is collision resistance even though you can find attacks on little h. However, this isn't a terribly useful thing. So, and you certainly don't, we will see in fact that people kind of relied on that to keep alive hash functions more than they should have. But that's one aspect of it. The other is that you could look theoretically at this again and say, are there conditions on the compression function weaker than collision resistance that allow us to show the hash function is still collision resistant? There's a similar sort of gap with regard to the padding of the message length as the last block. Remember, MD does that. We will see when we do the proof that we exploit that crucially. But nonetheless, that padding doesn't actually seem to be necessary for the hash function created by MD to be collision resistant. So if you have a compression function that satisfies maybe some different conditions, you may not need to append the length. And issues like that, both these issues are explored in the research literature. And there's a paper there you can look at. Okay, so here I recall the theorem again, and we're now going to prove it. So what does our proof have to do? We have to show how you design this attacker here, finding collisions for little h given collisions for big H. And it's going to be quite simple. We know that we can run this attacker on input the key k to get a collision for big H sub k. And let's call that M1 and M2. So hk of M1 equal hk of M2. We will simply walk through that block by block and find a collision for the compression function. So the pictures might look like this, but we'll break the analysis into a couple of cases. So just for illustration, let's assume the first message was 2 blocks long and the second just 1 block long. The hashing of the first message is just depicted over here. Remember that it will take the 2 blocks here, then append the length in blocks of the message, so here the number 2, and run the compression function each time, so a total of 3 applications of the compression function, starting with 0, and we now just give names to the different values of the chaining variable at the end. What the output is this, and it's of course equal to hk of m1. Now our adversary a sub little h is in possession of everything you see here. There are no secrets. It has the key k. It's handed m1 and m2 by the other adversary, so it can perform this whole computation. It knows all these intermediate values, the output values, the inputs, everything. And it knows that for both cases. Here there's just 1 block, so the number here is a 1, and the rest is as before, and we use the subscript here to differentiate which message it is. Okay, now our adversary a sub little h looks at this and says, I need to find a collision for this function. What does that mean? I need 2 inputs with the same output. Now remember that for this, an input is the whole thing of this form. This whole thing is 1 input because they're formally just concatenated. Now looking at this, our adversary immediately says, but I have 2 such inputs that collide. I know that this equals this. The outputs at the end are the same because m1, m2 is a collision for big H. So if I write down this as 1 input and this as the other input, well, the output is the same for both. So let x1 equal that, x2 equal that. Remember, this adversary can compute everything, so it knows these values and can do this. Then we know that hk of x1 equals hk of x2 because we know the outputs are the same. And so we're done. We are done, but one should note that the proof requires us to check one more thing, which is important. This is a collision only when x1 is different from x2. Why would that be true? Well, in this case, because this prefix and this prefix are different, a 2 and a 1 are not the same. So in other words, this is why we're looking at case 1 here, because the fact that the lengths are different is exploited here to see that these 2 inputs are different and we really have a collision. It is also where we exploit that we actually have these lengths present at all. So to summarize, we're done with the first case of the proof, the one in which the 2 collided messages that our adversary a sub big H provided have different lengths. But our adversary says, okay, it seems like you know how to handle that case. I'm not going to do that. I'm going to output messages of the same length that collide. And now what happens? Now our picture looks like this. Maybe we have both messages being 2 blocks long, and we've shown them pictorially in the same way. Again, remember that all the intermediate quantities can be computed and are in possession of a sub little h. Now, in the second message also, a 2 appears at the end here, and each iteration is 3 blocks. How am I going to find a collision? Well, in fact, the strategy used before is still correct. The fact is that looking at these 2 applications of h sub little k, little h sub k, the outputs are the same by assumption. So this input and this input do collide. So let's just do that again. We write down x1 as this whole input over here, x2 as this whole input over here, and we expect or hope that we're done. We'll simply return them because the outputs are the same. Would that be correct? It would, most likely, except there's a bit of a problem. What if these 2 values were identical? In that case, we would not win. So our adversary a sub h says, okay, so at least let me check if I win or not. If they're not equal, I'm done. Okay, so I can at least dispose of that case. So now I have to worry about their being equal. But notice that if they're equal, we can just effectively recurse. Why is that? Because it entails that this value and this value are the same. Why is that? Because x1 equals x2 and these are the second halves of them. If this and this are the same, I'm in exactly the same position as before with regard to these applications of h sub k, right? This application and this have the same output, and I can now see their inputs as a collision. So I do that. I take now this input as the first and this input as the second. So that gives me these two choices for x1 and x2. Okay, so am I done now? Well, the same story recurs. Hopefully they're different. If they're different, I'm done, I have a collision. If they're not different, then I have to pause. But then I repeat the argument. If they're not different, these two are the same, and I go back one more block. And now I have this input, and I return them. But at this point, one may say, well, but what if x1 and x2 are also the same? That, it turns out, is not possible because the messages m1 and m2 are assumed different. We have a non-trivial collision for the big hash function. And so if you walk through it, you'll see that once you get to this point, the only way for x1 to equal x2 would be that m1 equals m2. Okay, so that concludes our proof, and we've now established an important part of the design of many hash functions, including SHA-256. We have validated the iteration method used that applies the compression function to extend it to a hash function. That's not the only possible way to do this. One of the possible drawbacks for the MD method is that it's sequential, so you can't exploit multiple cores or parallelism to speed up hashing. So here is a depiction of a parallelizable way to turn a compression function into a hash function. And this only describes a piece of it. It says how you double the input length you're hashing, but you can iterate to do more than that. And the exercise asks you to validate this in the same style as the things we did earlier. All right, so to recap now, if we're trying to build hash functions, we've reduced the problem to the design of compression functions. So effectively now the big question is, how are we going to design compression functions which are collision resistant? That's our core problem. We will go back to a common principle that cryptographers have, which is to be conservative and use as much as possible what already exists and has been validated. And here, that would be block ciphers. Cryptographers have them, they've studied them, they've designed them. We know how to make good block ciphers. Why can't we exploit that? So let's say we have a block cipher with b-bit keys and n-bit blocks. B is the block length of the hash function. And so think of it as quite big, like 512, and n being 256. You have a block cipher like that, which you assume secure. And let's see if we can turn it into a compression function. And here's an obvious way to do it. Well, the compression function needs to take b plus n bits down to n bits. How can it do that? Let's use the first b bits here as a key, call that x, and the chaining variable, the rest n bits, as the message block. And then just run the block cipher with key x and input v. Okay, it's certainly a legitimate design, and it does the job of compressing. It's managing to take b plus n bits down to n bits, but does it work in terms of security? Well, let's see. So how would you approach this? We would put on an attacker hat and say, if I wanted to violate collision resistance, my task is to find two inputs with the same output. Each input is got two parts. So the first input is x1v1, the second input is x2v2, and I'm looking for this equation to be true. So can I solve this equation? Well, I have a ton of flexibility. I have 4 unknowns because I get to pick all 4 of these things, and I need to make this equation true. And I can do that because E is a block cipher. So in particular, here is an adversary which has advantage 1. It's very simple and fast, and the result is we can conclude this design fails to be collision resistant. How does it work? It picks x1 to be arbitrary, and the same for x2, and the same for v1. So this, and this are all picked to be some constant. Now we simply solve for v2. How can we do that? Well, we see, look at this equation and apply E sub x2 inverse to both sides. So we compute this as y over here, and then we run ex2 inverse on that y, and we get this value v2 over here. We exploit here that E is a block cipher, and so hence you can compute the inverse easily. In this case, because the key x2 is something we know. And then we return the collision. Okay, so it failed. Can we maybe think about what went wrong? Well, one of the things that went wrong is that we've always used block ciphers in situations where the key is hidden, but here it's not. And so we're trying to get security from a block cipher when the adversary already has the key, and we are seeing difficulties in that process. It uses here the fact that it not only has a key, but it can pick it itself and use that in the design. Now, just in case there's some confusion about this, the term key here is used in the context of the block cipher. It's not to be confused with the key of the hash function or compression function. Here we are talking about keyless compression functions and keyless hash functions. So the key input for the hash and compression function has simply been omitted just to model things like SHA-256. Okay. That key in any case would be public. It's not arising here. Okay, so now you would think that cryptographers look at this and say, okay, we better back off. Block ciphers are a bad idea in this context. They don't do that actually. They just make a minor tweak. What they do is that they define the compression function as apply the block cipher with x as key and v as input. But don't just stop there. Add back in the message block. So here you have n bits, and the sum is another n bits. So we look at that and say, well, there's not much of a change. We better try to see if that works. Is it still collision resistant? We can set it up the same way as before. We are seeking an adversary that finds inputs x1, v1, x2, x2, v2, such that this equation is true. We again see we have one equation with 4 unknowns. We get to pick every single unknown, and we need to solve the equation. Yet, despite all of that, it doesn't seem to be possible. So people don't have a way to figure out how to solve this equation. You can try. If you try the strategy we had before, you'll find that the difficulty is that if you try to solve for v2, you can't because it also occurs here. Effectively, there'll be a v2 on this side of the equation while you're trying to solve on this side, and it won't make sense, and so on. So this is another sort of thing that happens often in cryptography, is that you see something that doesn't work, and then you see that just a little change seems to make it work. So little things done the right way. Now, it turns out that there is history and validation for this method. So this construction is called the Davies-Meyer method, and that's used in MD series and the SHA-2 series, and thus in SHA-256. Except that one generalizes a little. For example, in SHA-256, you don't actually use an XOR. You use a blockwise addition modulo 2 to the 32. But that doesn't really change much of the elements of security. So now if we look back at SHA-256, we see that its compression function, as we saw there, was underlain by a block cipher. So that block cipher we had denoted in this way. And this being changed as we just described. So we've come to the point where we're able to at least understand or see quite a bit of that design from a quite general perspective. Next, we could ask, well, can we prove something about this compression function design, the Davies-Meyer construction? We know that constructions based on block ciphers do get proofs of security. For example, we proved that symmetric encryption modes of operation are secure, assuming the block cipher underlying them is a PRF. So PRF security of the block cipher implies security of the encryption in the IND-CPA sense. Why not try the same kind of thing here? Assume our block cipher is PRF secure and try to prove that this compression function is collision resistant. Would that work? The answer is that it doesn't. And the reason is there's a mismatch in the usage. And that arises because PRF security is inherently something about what happens when adversaries don't have the key of the block cipher. But here the key is X and the adversary knows it. And so PRF security just doesn't apply or help. Furthermore, there isn't just some kind of technical or philosophical difficulty. I can actually construct an example of a PRF secure block cipher such that this hash function is not secure. So although in practice this seems to work, it appears it works because of some property of the block cipher that goes beyond PRF security or is different from PRF security. This has attracted some research effort. For example, you can prove that this H is collision resistant if you assume E is what's called ideal. And that is a model rather than a definition in which E is just a random collection of permutations, one for each choice of key. It's an interesting open question actually to find some kind of what's called standard model definition of security for a block cipher under which you can prove that this H is collision resistant. That doesn't seem to be an elegant solution to that. So where are we now with regard to hash functions? Well, we have designs, we validated the designs to some extent, and we think certain designs are good, but we're still relying on the security of this block cipher. And certainly if that block cipher is weak in some way, there will be problems. If we want to see whether attacks like that exist, we have to actually look at the internals of the hash function and the block cipher and see if there's something exploitable there. So far, our discussion at least hasn't done that. What we've looked at in terms of attacks is only the birthday attack. And the birthday attack is generic. It never tried to exploit anything about the structure of the hash function. All it did was run the hash function. So are there any better attacks? If we start looking inside, and this is where we find interestingly that they have been found. So when the MD series was first defined, it looked pretty good to start out with. And yet today, the MD5 hash function, one can find collisions in a minute. There are algorithms to do that. The first indications of weaknesses arose already in the mid-1990s when collisions were found for the compression function underlying MD5 and in a reasonable amount of time. Now remember, what that means is that we have a proof that the security of this implies the security of this, right? So once this is insecure, does that mean this is insecure? No. It means our proof case guarantee has become vacuous. But it doesn't mean that attacks on this lead to attacks on this. Our proof said the opposite, that attacks on this lead to attacks on this. This led people to neglect this fact a little and say, okay, this means the proof isn't useful anymore, but this hash function isn't broken, so let's keep going. That turned out to be a bad decision, because by 2004, there were very powerful attacks on MD5, and they even got stronger. If you look at SHA-1, in 2005, there were attacks breaking it in time about 2 to the 69. And then in 2017, that was improved to about this much. But this is quite a bit short of the birthday estimate. Remember, that ought to be 2 to the power 80 because the output length here is 160. So this is well short of the security you would want, which is that the birthday attack is best possible. And this was demonstrated as feasible. So the collisions were actually found. And the result is that the hash function was phased out. So major vendors of browsers stopped accepting certificates based on SHA-1. The later functions in the SHA-2 series are still viewed as good. As far as we know, the best attacks on them are the birthday attacks. So this is an interesting illustration of how attacks on hash functions are exploited. Flame was a piece of malware that was discovered in computers in Iran that had been infected. It had something to do with their nuclear weapons program. And this malware internally was forging certificates by creating MD5 collisions. And it was doing that by exploiting a cryptanalytic attack on MD5, in fact, one that at the time wasn't even in the public domain. And so it had obviously been designed by some quite expert cryptanalysts. And there are, of course, speculations as to which government agencies or which countries had helped to create this malware. This is a depiction of the PDF files found by the SHA-1 collision finder. So they actually say, give us specific messages in the form of PDF files, and if you run SHA-1 on them, they have the same output. And you can read about that at the URL at the top there. This is a SHA-1 certificate. It's something you can see inside your machine. If you're using a Mac, you can get it through the keychain, and you can pull up. This is from my computer. It's something about when I visited UCSB, and it shows you how SHA-1 arises, which is that here the signature algorithm is SHA-1 with RSA encryption. And so this is the kind of thing that would now be no longer accepted. You see this announcement from Microsoft that they're going to cease support for any TLS certificate signed with SHA-1. And this, as we saw, attracted a lot of interest. Here's a popular post in which people are worried about the implications for Bitcoin. If SHA-1 has collisions, what does that mean for Bitcoin? Well, not necessarily a lot. Bruce Schneier explains the difference between collision finding and what happens with the use of hash functions in Bitcoin. So now we could step back and maybe ask this sort of provocative question that maybe cryptographers haven't done too well with hash functions, have they? MD5 was broken, SHA-1 was supposed to be better, and that was broken. Maybe the others we are looking at are bad too. What's wrong? Why can't cryptographers do better? So let's speculate about that a bit. So your question here is assess the job performance, and how would you grade cryptographers? They're doing great, they're doing okay, they're doing really badly, and forget human intelligence and let's have a machine learning algorithm design hash functions. Okay. So what would you pick? Well, I'll leave you to make a choice, and give some perspective that might lead to a view on this. Why don't cryptographers build secure hash functions? Are they ignorant, or what's going on? Well, there's of course a personal view, but my sense is that cryptographers are perfectly capable in principle of building very secure hash functions. The difficulty is the tightrope of performance to security. When you strive for very high speed, you cut corners. Now, SHA-256 runs at 3.5 cycles per byte on modern machines, and that's less than a nanosecond per byte, and hardware will make it even faster. These things are just ridiculously fast. To think that something this fast can have any kind of security is pretty wild, actually. So when cryptographers are trying for speeds like that, the performance factors enormously into the choices they make. And if you gave them a break and said, look, it's okay to have a 10-factor slowdown, add a factor up your rounds in the block cipher by a factor of 10, my guess is that it would be really, really hard to break anything they design. So this must be kept in mind as to how cryptography works. Okay, but in any case, we do see now that the SHA-2 series was seeing problems, and that led the National Institute of Standards to say, let's go a next step and let's design a new family of hash functions. So just like with AES, they did this through a competition. They put up a call for submissions where they designated some parameters. The functions in the family should have different output lengths, so you have a choice of output lengths. And they should be collision resistant, but also have other security properties. And of course, as usual, they bump up the performance requirements. They have to be at least as fast, if not faster, than SHA-256. So you can look at the URL here for the competition, and submissions poured in from all over the place. There was a total at first of 64 submissions. In the first round, they just threw out some that had immediately obvious weaknesses or failed to meet requirements or weren't properly documented. So there were 51 serious submissions left. And now, again, the same process started where NIST told the cryptographers to go break each other's designs and see what was left standing. But also, of course, implement all the designs and compare performance. And based on results from that, after some time, a second round started in which 14 advanced forward. And these were the ones listed here. All of these were good hash functions, and now there was an even more serious effort at whittling down to some finalists. So again, people tried very hard to find attacks, compare performance on many different platforms, and so forth. And after some time, 5 finalists emerged, which are the ones here. And in a final thrust, SHA-3 was selected to be the Ketchuk hash function shown over here. Lots of cryptographers around the world were involved. UCSD was involved, at least here, I think there are 3 submissions in this group. I was involved in one of them, which is the Skeen hash function, which survived until here, but dropped at the end. By the way, the reason wasn't security, it was hardware performance, and that Skeen was not good enough in. The empirical rule of thumb, by the way, that summarizes how these competitions work is the fastest unbroken design wins. So roughly, when things all look secure, they'll pick the fastest one. So here's a quick look at Ketchuk at SHA-3. And interestingly, it doesn't use this MD paradigm. It doesn't have a compression function in that form. Its core primitive is a permutation. So F here is a public permutation, not a keyed one, not a block cipher. There's no key, a single function taking some number R plus C of bits into that many bits again. Okay. And the way the design works is that you start from kind of a state variable of 2 parts, R bits and C bits, initially both 0. And you start iterating. In each iteration, you first add in some message blocks, a message block, and run F. Then you add into the top part another message block and run F. The message block's always entering the top part. The second bottom part, nothing is entering. The message is, of course, padded here so that its length is a multiple of whatever length you need to do this XOR, which is R bits over here. Now, when you're done with that, you don't output this result because if you output everything, you could reverse, because F is easily invertible. It has no key. Anyone can invert it. Instead, there are more steps in which you do a truncation. You simply throw away some bits of the output, and that seems to be good. There are primitives constructed from this that are worth maybe knowing about. We have an extendable output length function. There's a way to get a function which, given an input message n, returns any number d of bits you want. That's a very nice sort of tool to have.